Okay, so just a quick recap from last time. This is where we were. We are looking at image classification as our canonical problem to develop a lot of these techniques with. Our image is going to be some input X, and we're asked to predict an output Y from a list of categories. We are asked to write this function that takes in this image, returns this label. We do not know an algorithm without data that does this job well. And so our approach is going to be the supervised learning approach, which follows this particular paradigm, that there is some unknown target function f that does the mapping from X to Y. We will ask for a data set of XY annotated pairs. We will define a model class or a hypothesis class, which is a set of allowable mappings from X to Y. You will meet such a mapping today, such a set of a model class today. We will define a loss function, which characterizes how good is my model with respect to my data D. And ultimately, we will follow this up with learning, which is just search in the hypothesis space. So find the best H in the model class, find the best member of the set of functions that I've defined with respect to the loss function that I've written down. That's going to be the paradigm. We introduced this notion that as soon as you define a model class, typically this makes sense with parametric model classes, where every entry in this model class is some parameter W. You right out the bat pay something known as modeling error, which is the best you could have done in your model class with respect to reality. There is something known as estimation error because you do not actually find this best W star. You find something else because of finite data sets. And there is a third source of error, which is optimization error, which is, this is the W that we actually estimate and find due to our actual optimization procedure, SGD, early stopping, any other steps we may have built in, non-convexity of the loss functions and things like that. So that's the sort of error decomposition that we introduced last time. Today, we will see an explicit instantiation of it. The first classifier that you met last time was nearest neighbor, which basically we forego all learning. We just memorize and store all data and labels and predict the label of the most similar training example. We showed you qualitative examples of what that looks like in CFAR10, that these nearest neighbors do actually have some, even in pixel distance space, have some intuitive gist of the image being captured. Therefore, there is some hope that the labels might be able to be copied over. We told you about 4 different quantities that if you can specify them, you are basically specifying a memory-based learner, the distance function, how many nearest neighbors, whether you're going to weight them, and how are you going to fit the local points. And we introduced 1 and k nearest neighbors by specifying these points, the answers to these 4 things. And then we, of course, taught you how to pick hyperparameters like what is k, what is the distance function that you use, and anything else, which is break your data set down into a validation fold, or if your data set is not large enough, vary the validation fold around across multiple splits and search for settings of k and hyperparameters so that they maximize performance on this validation set or validation fold. And then use those hyperparameters k star to report performance on test. And that's it. Do not do any optimization on the test set. We also told you about the problems with instance-based learnings, that it's expensive. It does not work well when there are a large number of irrelevant features, and the problem of high dimensional data. And we have some notes up on the webpage where you can read more about this. Okay. So this was a quick recap of last time. I like doing this because this puts us in the right mental space. I can pause here if there are any burning questions about anything that wasn't completely clear about last time. Today, our goal here is to talk about linear classifiers. It's a new model class, and 2 specific loss functions which define how well we're doing in a particular model class. So I can pause for a couple of seconds to see if there were any questions about anything we covered last time. All right, so let's dive in. So we're going to start with linear classification. Dropped out. We're going to start with linear classification, and this is really the simplest parametric family of classifiers that you can construct. And one thing I want to say is that linear classifiers may appear simple, but an intuition we're going to play around with a lot is that in deep learning and neural networks in general, we're going to view a lot of these things as Lego blocks or building blocks or layers that you can attach in a broader architecture. So even though by themselves they may appear simple, they are going to play really important glue roles in more sophisticated networks. If you ever approach a data set where there's not a lot of data available, you should definitely start with linear classifiers because they're the simplest ones. But even in domains where there is a lot of data available, you will often find linear classifiers or linear layers stuck in between as glue. So one example of this is in the visual question answering example that we showed you last week. And interestingly, one of the simplest or the earliest architecture for this problem was that you're given an X, or in this case, you're given an image and a question. And the way these architectures are constructed is that the image is converted into a 4096 dimensional representation. Think of this as I in some R to the D1. This is by taking the last the activations from the last layer of a standard architecture called VGGNet. We'll teach you what convolutional neural networks are. Don't worry about the details here. And for the question, this is embedded again into a vector space by an architecture, a recurrent neural network called LSTM. We will also teach you that later in the class, so do not worry about those details here. Think of this as giving you Q in some R of D2, I in some R of D1, which are then concatenated as representations of the image and the question. And after this concatenation, you have a linear layer that is giving you scores and probabilities for over a space of answers. So this stuff, the CNN and the RNN are complicated things, but after that, you do actually have a linear layer that follows in this. After these embeddings have been computed. So that's what I was talking about as glue layers that show up at various pieces. Okay, so let's start making this concrete. We are going to again pick up our data set CFAR10. There are 50,000 training images. Each image is 32 by 32 by 3. There are 10,000 test images. Here are the 10 categories. Last time what we had done is that with nearest neighbor, we had said we're just going to not do any learning. This time we're going to explicitly define a parametric family. So remember our hypothesis set, the set of all acceptable mappings from X to Y. Here is the simplest way of defining that model class. The way we're going to define this model class is, I said this is a mapping from X to Y, but I'm actually going to do something simpler. I'm going to say, instead of actually giving me an integer, which is a class value, I'm actually just going to ask for 10 numbers, which are the class scores. So S1, S2, all the way till S10, because there are 10 classes. And these are just the numbers I'm going to ask for. So I'm basically asking for a mapping for a function X, which can depend on some parameters W, that give me this vector S of scores, 10 scores or K scores. And the simplest way of defining this mapping is to say that this is a linear mapping. So X is my image. So I'm going to show this in a second, but I'm going to convert X, which has 32 by 32 by 3. I'm going to convert this into one long array. So the product of these three is 3072. I'm going to convert this into one long array of size 3072. I'm going to multiply that by a matrix W, and I'm going to add a vector B. And that is a linear classifier. That's a linear mapping. And this right here is my hypothesis class. It's a way of going from X to Y. I haven't actually told you how to get to Y. This actually gives you scores, not labels, but that's just a detail we will get over. And now you can see that the space of all possible functions is parameterized by the space of all possible w's and b. So not all functions are allowed, only certain linear functions are allowed, but we've defined this nonetheless. Let's do just some quick dimension analysis and size analysis. So X, which is our image, has 3072 dimensionality. So there's 32 by 32 by RGB, 3 channels. So X is 3072 by 1. W has this size of 10 by 3072 because it has to give you 10 scores, and it has to accept a vector on the right for multiplication of size 3072, and B is also a vector of size 10 cross 1. And this gives you S, which is a vector of length 10 cross 1 again. So that's the dimensionality analysis that's happening here. Okay, so this is our linear classifier. Here's an example, a visual example of that, where we can actually take a really small image with 4 pixels and restrict our attention to just 3 classes. The reason why we're doing that is because it is easy to draw pictures with 4 pixels and 3 classes, and we can actually see the matrix, but the same analysis carries over. So let's say that there are not those 3 channels. We've restricted our attention just to an RGB image. This is pixel number 1, 2, 3, 4. We have done a row major rasterization of this into this particular vector. So this is our X. So 56 is living in the first dimension, 231 is living in the second dimension, 24 is living in the third dimension, and 2 is living in the fourth dimension. So we've stretched this image out into a column vector. And if this is that stretched out thing in the column vector, W, because we've restricted our attention to 3 classes and because there are only 4 pixels, W is of size 3 by 4, B is of size 3, 1, and score is of size 3, 1 again. So this is that example restricted to 4 pixels and 3 classes. Now, as soon as you do this, it becomes clear that you can start visualizing what's happening. What's happening is that if I want to construct the score for any particular class, I take my image, I string this out into a long vector, and I can take a dot product with this row, because this I can think of as W cat transpose, right? This is the weights corresponding to the cat class for each of there are 4 dimensions of this because there are 4 pixels, and I take a dot product of W cat with respect to X, and that plus B sub cat, where if I define this is the B sub cat dimension, that gives me the score for the cat category, right? And I can repeat that for any of the other classes. So the rows of W corresponds to classifiers of each of these categories. Okay. There's just a quick side note that this vector B can in fact be incorporated as an additional column or as the 5th column of W by just adding another dimension to X. This is a fairly common trick. If you've probably seen this if you've taken a machine learning class, you've seen this in SVM lectures maybe, or logistic regression lectures. So it's fairly common that you can write W transpose X plus B as W B X1. This is a fairly common way of if W is a scalar, a vector as opposed to a matrix, and this is the same expression of that for a matrix, that we can add a column and stack the B column and add a 1 to X, and it's accomplishing the same expression. Okay. So therefore, if you don't see B explicitly written out, don't worry about it. It's just, I will write it out explicitly, but if in certain texts at other places, you don't see B explicitly written out, it is there. It's implicitly there as the lost column of W. And you should just make sure when you use a software library, you should check if it's asking you to explicitly pad X with an extra dimension of 1, or the software library will implicitly pad X with an extra dimension of 1. You should just make sure that the APIs are compatible with your expectation. Okay. And so back to our error decomposition, where we are is that we have essentially written down a model class. So instead of a deep neural network, we're starting with a fairly shallow linear classifier. Every point in our model class is W matrix, comma B vector, the bias vector and the weight matrix. That's the point in this. Every point in this corresponds to that. And so now what we're asking is, what is the best W and what is the best B that can fit this reality, this mapping from X to Y. And now it becomes clear why why this picture is probably right, that reality does not live inside your model class. This mapping from X to Y, linear in pixel RGB intensities, feels odd. That it's not clear that that would be the case. That's the true underlying function. Okay. There's a comment, B is the bias, so basically the y-intercept, otherwise we have to cross the origin with our line. Yep, that's exactly right. That is what the role of B is. Okay. So this view of f of x is equal to W transpose x plus B, you can think of this as the algebraic viewpoint of this linear classifiers, right? That they are linear, well, because it's a matrix multiplication. That's why they're linear. At the same time, there are other viewpoints that we can construct. As soon as you start, one other viewpoint that you can construct is, you can say that just like images can be rasterized or reshaped into columns. So just like we can take this 2x2 object of an image and we can construct a long vector, we can actually take each row of W and reshape it into a 2x2 matrix. So what I've done here in this 2x2 matrix on the right, 0.2, -0.5, 0.1, 2.0, this is essentially the first row of my W matrix. So I should think of this as W cat, except I've converted it into a 2x2 size, right? As opposed to a long vector. And this is my B cat, if you will. And because I can reshape the rows of W into the same size as my image, now this exposes that the dot product that was happening between the rows and the columns can be viewed as a template matching, that I basically place a filter of the same size as the image on top of the image, and I multiply all elements that overlap. So 0.2 times 56, -0.5 times 231, and so on, and I add a bias, and that gives me this score. That way of viewing things tells me that I should be able to visualize these W's. So this is that visualization right here. So this is that visualization. What I've done is, for each of these 10 categories, this image is actually a height by width by 3 image, right? So this image is a tensor. Therefore, this W is also can be reshaped into that tensor, height by width by 3. And what I've done is, for each of the plane category, car category, bird category, I've taken the weight row, and I've converted that, and I've visualized them here. This height by width by 3 weight matrix has been visualized as an image for each of the categories. And as soon as you do that, you can start to see that these weights or these templates are capturing something about our data set. These are learned weights. This is after learning has been done, after optimization has been done on this data set. In fact, you will plot such visualizations in homework 1. And you start to see things like, a car is basically a red blob on top of a darkish blob. Maybe the darkish blob is representing the wheels, and maybe there's a grayish blob on top, which is representing the windshield. The plane is like a darkish blobby thing with blue all around, which seems to suggest that all the pictures in this data set were ones where the plane is against a blue background. Because this sort of intensity has to multiply the picture intensities, and therefore when things align is when you would get a high score. So this is telling you what it's looking for, if you will, in these classes. This also tells you that, for example, if you look at the horse classifier visualization, sorry, these legs, I'm hallucinating here, but there appears to be at least two head sort of shapes appearing in the horse classifier. And that's, one intuition for that, and one reason for that is that what's happening is that there may be in the data set, there may be some horses that are facing to the left, there are some horses that are facing to the right, and basically there aren't any weird angles of horses, there aren't any top-down pictures of horses. And that's or at least if they are, they're not the majority of the data set. And so that's what our learning process has extracted out of this data set. So all understanding of these classes from the data set have been compressed into these templates. And these templates then multiply any new image. And so whenever these templates match that new image, you're going to get a high score. Whenever they don't match the image, you're going to get a low score. And that's what we've extracted as a process of learning. And so this is a visual viewpoint of the linear classifier. I'll pause here to see if there are any questions. Let's proceed. So we've shown you an algebraic viewpoint. We've shown you a visual viewpoint, and the third one is a geometric viewpoint. And so the geometric viewpoint basically says I can take the W matrix, I can think of this as the W car row of this, and I can view this as W transpose car X plus B, and I can think of this as a particular line, right? So that's this line. So if I had two-dimensional features, this is obviously a low-dimensional representation. In reality, we don't have two dimensions, so we can't draw this on a plane. But let's say there was just x1 and x2. If that was the case, W transpose X plus B, if B did not exist, W transpose X plus B would pass through the origin. So this would be the W direction. W transpose X plus B would pass through the origin. This is, for example, W car, the vector. Anything in this direction or anything orthogonal will get you 0 score. And that's why this line that we're seeing is the line of W car transpose X plus B equals 0. So any time an image lies on this line, you get 0 score. On this side of things, you might get a positive score. On this side of things, you'll get a negative score for the car. And then there are similarly deer classifiers and airplane classifiers and other things. So we're basically carving up our feature space as into various pockets where you either lie on one side of a hyperplane or another. Okay, so the geometric viewpoint also immediately highlights certain problems. So for example, if you ever end up with data distribution in a two-class problem where positive classes live here, negative classes live here, there is no hyperplane that you can draw that will put all positive classes on one side, all negative classes on the other side. Similarly for these other shapes where you might have positive classes living in a ring around the data in the original and negative classes otherwise. This is a fairly common occurrence that you will have, for example, clumps of your data scattered through the feature space, and this usually happens in multimodal distributions. So there is, you're trying to define when does this alarm fire, and it fires either when this condition is met, or that condition is met, or that condition is met, and those three are very different kinds of conditions. And so they live at different parts of the feature space, and it's hard to draw a single line that captures all of them as on the positive side, but while also making sure that no negatives are captured on that side. And this also happens in visual recognition, where there are subcategories of objects, and those subcategories form clusters that are spread apart, with negative clusters being in the middle. Okay, so these are the three viewpoints: the algebraic viewpoint that presents to you matrix multiplication, the visual viewpoint that presents to you this idea that there is a template per class and that we can visualize those templates, and you should when you train these classifiers. In general, I highly recommend diving into the data, looking at things and building intuition. And the geometric viewpoint, which says that there are hyperplanes, and that also tells you what you might expect to happen to various categories. Okay, so far what we've done is we've defined a scoring function. We have defined a model class, W transpose X plus B. And we've given you example scores for 3 images for some W. So if I just come to you with a W and B, and there are 10 categories, I will give you score vectors for these 10 categories for each of these 3 images. And our job is now to tell whether this W and B is good or bad. Is this a good W? Is this a bad W? Well, this particular W seems to assign 2.9 score, and these scores are real valued numbers, right? They're not probabilities. They're not between 0 and 1. They're just arbitrary numbers. So it assigns 2.9 score to the cat class. We can see this as a cat class, but there are other categories where higher scores are assigned and similar. So this one doesn't seem to be a particularly good W. So our job is, well, how do we tell what's a good W? And so we have to define a loss function that quantifies our unhappiness with the scores across the training data. And then we have to come up with a way of efficiently finding the parameters that minimize the loss function. So that's the optimization part that we will not do today, but we will define a loss function. In fact, 2 loss functions today for quantifying how good is W with respect to this data set D. And notice again, I'm not writing explicitly B, but yes, B is also implicitly here. It's just this form is common and appears over and over again. That how do we know how good W is with respect to this data set? And going back to our supervised outline, we have defined now a model class. It's a linear set of functions. We are now defining a loss function. How good is my model with respect to my data? Okay, so loss functions. One thing I want to mention about loss functions is that for a long time, I thought this idea of writing down loss functions that we minimize as opposed to reward functions that we maximize was sort of like a pessimistic versus optimistic viewpoint. That instead of minimizing loss and counting how badly you're doing at all points of time, we should be maximizing sort of reward or happiness or how good things are. That this felt a lot more optimistic. And over time, I've realized that I think the reason why min loss is better as opposed to max reward is in some sense the scientific method tells us that all we can hope for is to be less wrong. We don't. The scientific method tells us that we have theories for physical phenomena, and our theories are increasingly less wrong, and that they explain certain parts of the phenomena. You can never actually prove that your theory is right because there may be some evidence out there that disproves your theory, and the lack of that evidence is all that you can hope for. And over time, I've come to appreciate this, that being increasingly less wrong is all we can hope for. And so I've come to change my view on that. Just a random thought on that topic. Okay, so suppose we have 3 training examples and three classes. This is again just for simplicity. There are cat, car, frog. Here are the 3 images. Here are the scores. Now I come to you and I say that a loss function is with respect to a data set. This is always important to remember, that a loss function is not, or a loss value is not defined with respect in isolation. It is defined with respect to a data set, and we're going to use these factorized losses that factorize over all examples in the data set. There are certain loss functions that are non-factorizing, non-modular, if you will, that are defined at the corpus level, but we will largely not talk about them, at least initially. So there is L sub I. This is our scoring function. SI. So for the ith example, this is the vector of scores. This is I equals 1, this is I equals 2, this is I equals 3, and so on. And we know what the true label for these things are, and we have to decide, given this vector, how good is this, right? So here, for example, there's a 3.2, 5.1, 1.7. We can see this is a cat. Car has a higher score. How do we quantify that? So the first quantification we will do is through something called the multiclass SVM loss. This is a generalization of binary SVMs. If you've seen them in an intro to machine learning class, the same intuitions apply. Let me, instead of just throwing this formula at you, let me start diving into a bit of the detail. Here's how multiclass SVM loss is defined. It's a bit, I've written the entire expression down, but let's walk through this. So L sub I, for the ith example, we are writing down the loss of the ith example. There is a summation on all categories. So this is j equals 1, this is j equals 2, this is j equals 3, and so on. So there's a summation over all categories that are not the right category. Let's put that aside for now. We're summing over all the other categories. And what we're saying is, if the score of the correct category, so this is score of correct category, we know that the correct category is cat. If the score of the correct category is greater than the score of any incorrect category plus a margin of 1. Why 1? If you remember your SVM lectures, turns out this is just an arbitrary scale-free quantity. 1 can be replaced by any epsilon, which is strictly non-zero, and the entire sort of optimization problem will scale up or down. So let's put that aside. 1 doesn't really matter. It can be replaced by any non-zero constant, any positive constant. And what we're asking for is that this score of the correct category should be greater than the score of this other category plus something, plus 1, a margin for simplicity. So 3.2 should be greater than 5.1 plus a margin. It is not. 3.2 obviously is not, but that's what we'd like. If that is the case, then the loss will be 0. So we are happy if the correct category is scored higher than the incorrect category plus some margin. But if that's not true, then we're unhappy. And the degree to which we are unhappy is exactly the violation. So the score of the incorrect category minus the score of the correct category plus 1. So this is how much it would take to make us happy. Because if this number, if S of Y was in fact greater than Sj plus 1, then this value would become negative. And that's why this otherwise condition would not apply. So there's an if-else condition happening here. We'd like the score of the correct category to be greater than the score of the incorrect category by some margin. And we can express this if-else condition by a simple max operation. So a max of 0, x function is something that looks like this, where this is x. When x is positive, it's just the y equals x line. When x is negative, it's just the y equals 0 line. Right? So this is what that function looks like. It's basically a way to easily express if-else conditions. And generally, max, min of linear things are, you can think of them as expressing if-else conditions. And it's a common trick to keep in mind. Okay, so max of 0, sj minus s sub y plus yi plus 1. This is our loss, and we sum this over all j's, so all other categories other than the ground truth category. Let's take a look at an actual example. Oh, yeah, by the way, this is known as the hinge loss. It's known as the hinge loss because if you plot the s sub y plus, so L sub I versus s sub y plus 1, if you plot that function, it basically starts off positive and at some point it becomes 0. And that some point is sj plus 1 value. And this looks like a door hinge from the top. And that's why it's known as a hinge loss. So let's look at and because we're summing over all other categories, this is the intuition that we're going for, that if there's a one-dimensional scoring, if we project all scores for all categories on the number line, we want the score for the correct category to be, and these are the scores for the incorrect categories, we want there to be a margin. And that as soon as the score for the correct category is greater than the score for the incorrect categories by a margin, all of them, then this summation would also result in a 0 because each individual term would be a 0. Okay, so let's work through an example. We are looking at an example. So here's the numbers on our slide: 3.2, 5.1, 1.7. There is a summation over all other categories. So there are two terms in the summation. First of all, we're doing a max of 0, compare 5.1 and 3.2. So 5.1 minus 3.2 plus 1. Sj minus sy sub I plus 1, and our intuition is satisfied that we're not happy with this. 3.2 should have been greater than 5.1. The score for the cat category should have been greater than the car category, but it is not. Because it is not, we're going to be left over with a max of a 0, 2.9, and that 2.9 will survive. This comparison, on the other hand, 3.2 is greater than negative 1.7. So when we compute the other direction, negative 1.7 minus 3.2 plus 1, we're going to end up with a max of 0, 3.9, and therefore 0 will survive out of that max. And so the total loss, so the unhappiness value L sub I for this image is 2.9. That's how unhappy we are with the W function here and the W and B that's giving us these things. We can repeat this for the other image. So here, this is a car image. The car score is 4.9. The cat score is 1.3. The frog score is 2.0. Our intuition, this intuitively feels right. And if you compare the numbers, yes, 4.9 is more than a margin of 1 from 1.3, and it's more than a margin of 1 from 2.0. So the loss should be 0. And if you just run through the math, that actually does turn out to be the case, that you end up comparing 0 to a negative value, 0 to a negative value, so 0 survive out of the max, and you get 0. So our intuitions are satisfied that L sub I here is in fact 0. That's a good thing. Is hinge loss graph the graph for summation? Yes, that's the plot I showed. That's L sub I as a function of S sub Y sub I. So loss function can never have negative value. Interesting question. Give it a slide. We'll come back to this. Okay. Right. So this is the example run through for the third image. I won't repeat the discussion. It's basically the same sequence of steps. And then ultimately these are the three, L1, L sub 2, L sub 3 for the three images. We sum them together, divide by 3. This is our average loss for this data set of three images. This is how unhappy we are with our current setting of W's and B's with respect to this data set. And we're trying to drive this number down to 0. We'd like this to be small, or at least as low as possible. And we'll talk about how low you can go. Okay, so time for a couple of questions. If you've been paying attention, feel free to type this in the chat. And so here's the question. What happens to the loss if the car image scores change a bit? And this is the car image. If I just sort of go in, add a plus minus epsilon 1, plus minus epsilon 2, plus minus epsilon 3, where these are very small numbers close to 0, what happens to the loss if I do that? Basically, what's happening is that there's no change because if you look at Sj minus S sub Y plus I, there was sufficient margin here. 4.9, 4.9, the margin with respect to 2 was greater than the margin of 1. So epsilon perturbations do not trigger this gap between picking 0 versus picking something else. And so this is what you would call stable or robust at these current values. Small epsilon perturbations, if epsilon is small enough, does not make any change. The same actually cannot be said for the other images. You will actually perturb it by epsilon in these cases, or epsilon 1 minus epsilon 2, depending on how exactly you're writing it. What is the min/max possible loss value? At initialization, W is small. So let's say we are trying to start our training, and W is a small value. And so at initialization, all of these numbers start at around 0. The scores for all, when you multiply the X, When you multiply a zero matrix by any x, you're going to get nearly zero. Because it's nearly zero matrix, you'll get nearly zero scores at initialization. Let's say you do that. If so, what is the loss at initialization? So you'll get number of classes minus. Okay. And what if the sum was over all classes? I'll go a little bit, I'll answer this. I won't take the questions for this. I'll just answer this myself. What if the sum was over all classes? So instead of this summation, excluding y sub I, if we had also included that in our summation, all that would happen is that we would end up comparing s sub y sub I to itself. So this quantity would be 0, but this quantity would be 1, and that would be constant for all I. So we would just end up adding a plus 1. So we would just take our L sub I and we would replace it by L sub I plus 1, which does nothing to the optimization. You're just shifting the loss value up by a constant. What if we used mean? So instead of the sum, instead of this summation, if we had just divided everything by the number of classes k, nothing happens to this as well. You're just scaling your loss value by a constant. It does not depend on W. It does not depend on your model class. It's just a constant that you're scaling this by. So it plays no role in the optimization. And final question, at least in this series, what if we found a W such that the loss was 0? What if we could take this loss over all example, sum over all classes, max of 0, comma, this minus this plus 1? What if we found a W such that loss was 0? Is this W unique? Let me take, this is a simple one, so let me take, wait for answers here. Do people think? And no, that's exactly what we worked through. Here's an example that I've written down. In the interest of time, I'll move forward, but it's essentially, the same numbers, plugging in twice of those, you'll see that you end up with exactly the same analysis. And here is a really simple implementation of this loss function. This is a vectorized implementation where you're doing W transpose X. You're setting the score differences, and just making sure that for yourself you're setting it to 0, so that you're handling this part in this line. That you have to not sum over the ground truth categories, and you're just returning the losses. This is a really simple implementation of this loss. Okay, so here is a second loss function that we're going to introduce. We've told you multiclass SVM loss or multiclass hinge loss. Now there's a second loss function that we want to teach you, which is, but in order to get there, we will introduce something called the Softmax classifier and a multinomial logistic regression model. You may already have seen this in an intro to machine learning class. We'll make sure that we cover the basics, but let's look at this. So right now, remember that these are all scores. They're uncalibrated scores. They're just numbers between negative infinity and positive infinity. These are not probabilities. We explicitly made a case of that. But what if we wanted probabilities out? Could we shoehorn this into some sort of a probability? And that's usually where the softmax function comes in. You will meet this function in homework 1, I believe, either homework 1 or homework 2, but you have already met the components of softmax, the log sum x function, in homework 0. And softmax basically says, what I'm going to do, it is this sort of a function that if you give me the score vector, in order to give you the probability of any class, I'm going to exponentiate the scores and I'm going to then normalize. Visually, that looks like this. So I have a list of scores. I'm going to raise each of them. So e to the 3.2, e to the 5.1, e to the negative 1.5, and that gives me these numbers. These are unnormalized probabilities. They're all positive because they've been exponentiated, but they do not sum to 1. And so we're just going to project them onto the simplex by saying that we're just going to divide them. So we're going to sum them up, divide them by the sum, and that's going to give us these numbers. Notice that 164 was pretty large, 24 was large, 0.18 was small, so that just got squished down to a third decimal or fourth decimal value, which we're not showing here. So the probability of this image being a cat is 13% roughly, or 0.13, and of being a car is 0.87, because we've exponentiated these scores and we've summed them, we've normalized them. And that is written as this function right here. And notice that what you'd like to compare this to is then a ideal function, or the ideal distribution, which would be 1, 0, 0. So this would be P star, if you will, and this is your P hat, your predicted probability. P star, we are putting 1 in the ground truth location and zeros everywhere else, because you have, in your annotated data set, you have no uncertainty about what the true category label is. And if you did have, what is K here? Oh, sorry, it's just a enumerator over the categories. If you want, so you can use any symbol here. It's just K equals 1, 2, 3. So this is just an enumerator over the number of categories. In this data set, you did not have any uncertainty about the categories, but if you did want to express uncertainty, P star could be non-one hot. Okay, the next thing, so just to give you names, this is the unnormalized log probabilities, or logits, as they are also known. These are unnormalized probabilities, and these are probabilities themselves. The next thing that we're going to do is we're going to use these probabilities to define a loss function. And the loss function we're going to define is negative log probability of the correct category given the image and W, obviously. So negative log e to the score of y sub I divided by sum of all the exponentiated scores. You may have met this object before in a machine learning class. You may have heard of things like maximizing the log likelihood, minimizing the negative log likelihood, maximizing the log this is, maximizing the log probability of the correct class. These concepts are all related. These concepts are all essentially the same. And the way to view them as how are they related is through an object, which is the KL divergence. And so let me actually just finish this example, then I'll do the KL divergence bit. So our running example says we have 3.2, 5.1, negative 1.7, 24, 164.18, converted into probabilities 0.13, 0.870. The loss we're going to define is negative log 0.13, because that is the probability that our model is assigning to this image, which we know has y sub I equals cat, right? So we're pulling out the probability of cat and we're doing a negative log probability of that. So 2.04. Remember that, log x is a function, or log p. This is p, log p is a function that looks like this. That's the general shape between 0 and 1. So negative log p is a function that looks like this. And we are concerned with its domain between the domain of 0 and 1. So probabilities are going to be values between 0 and 1. So it's going to start high, start falling as the probabilities come down, and the minimum value that can achieve is 0. Okay, here is one way of connecting log likelihoods to KL divergence to a term called cross-entropy, which you may also have seen. KL divergence is an object that you met in homework 0. Let's connect them together. And we'll connect them together by the same thing that I wrote out in a couple of slides ago. We're going to define P star as a one hot function where we're going to put 1 in the location where the correct category lies. So this is the true distribution. This distribution has no uncertainty. It could have uncertainty, that doesn't really matter. But this is our true distribution. It's indicating what we know about our labels. And I'm going to write p hat as the predicted distribution that our model is producing. I'm going to take from our model the probability of y equals 1 given xi, comma w, probability of y equals 2 given xi comma w, and probability of y equals, the all classes, the last class xi comma w. So this is the output of the softmax function. And then what I'm going to ask for is the KL divergence between p star and p hat. This is what your model predicts. This is what reality is. And what I'm going to ask for is to minimize this with respect to w, and yes, w and b. Notice that if you relate this to our picture, w, so this is your hypothesis set, reality is p star, it maybe lives outside. You are asking for the best approximation of that, and the error metric you're using is KL divergence. So you're asking for the best model in your model class that minimizes this KL divergence. Why? Oh, there's a question called why do we take negative log? It'll be very clear in a second. Why KL from p star to p? Why not KL from p? Why KL from p star to p hat? Why not from p hat to p star? Because you in homework 0 showed that directionality matters. It'll become very clear in a second, and the other directionality will often lead to algorithms that are often not correct. So this is a high-level answer. We will get to it later in the lecture. For now, not later in the lecture, later in the semester. For now, trust me that this is the right direction. There are two directions in KL. There's generally a wrong direction and a right direction. Trust me that this is the right direction. So we want to minimize this KL. Let's write down the KL. What does the KL look like? Well, we're summing over all categories of p star of y log p star of y divided by p hat of y. And this can be written as sum over y, p star y log p star y minus p star y log. Okay. Now, just to make sure everybody's still with me, somebody want to tell me what this first term is? Does this remind you of something? So this is negative entropy of p star is the first term. What about the second term right here? Definition of cross entropy of p star with respect to p hat. And so now it becomes clear that minimizing KL is the same thing as minimizing cross entropy, because the first term, which is the entropy, does not have any dependence on your model. It does not depend on W. It's an entropy of reality. In this case, by the way, the entropy is 0 because there is no uncertainty in P star. It's a one-hot distribution. P log P will give you 0 for all values because we define 0 log 0 to be 0 and 1 log 1 is 0. So there is no uncertainty in this distribution, but even if there were uncertainty in reality, it doesn't matter because that uncertainty is not a function of your model class. So finding the best model in your model class is the same thing as minimizing cross entropy. And that's why you might read about, we have cross entropy loss in our model. That's what they're doing. When they're minimizing cross entropy, they're searching for the best model in the model class by minimizing KL. And it should be clear that we can actually simplify this a bit further. P star is one hot, right? It's just ones and zeros. So everywhere where there are zeros, this summation will drop out. So the only thing that will be left is negative log P hat for the y sub I. And that's the only term in the summation that will be left. And that's why we are minimizing that over W. So minimizing KL is the same thing as minimizing cross entropy, is the same thing as maximizing log probability of the correct class. Okay, so this is the connection between log likelihood, KL divergence, cross entropy. Let's return back. So that's why we implement this loss function. That's why there's a negative here. And let's just work through this loss function as we have with the other loss function. So this is so let's ask, what is the min max possible value for L sub I? We're going to exponentiate the scores and we're going to normalize them. What's the lowest we could get, and what's the highest we could get? Inf. Okay, so here's another question. At initialization, all scores will be approximately equal. So let's say, we do the same thing where we initialize the W matrix to be an almost zero matrix. It goes ahead and multiplies with X, and so all these values are nearly zero. So all the scores are nearly zero again. What is the loss at initialization then, if all the scores are zero? Remember, here's what we're doing. We're exponentiating the scores. We're maximizing, taking a negative log where the numerator is coming from the correct category. So what is L sub I for at initialization? And L sub I will be the same regardless of I. Because basically when scores are zero, when you exponentiate and normalize, all the probabilities that your softmax will predict will be 1 over k, where k is the number of classes, 1 over k, because e to the 0 is 1, and you'll normalize that. So you'll get a uniform distribution, and you'll take a negative log 1 over k for all examples. So you'll get log k, where k is the number of classes for all of these things. So log c, if c is the number of classes, 10, in this case 2.3. This usually ends up being quite a valuable sanity check because if you, so the two losses we introduced, we told you what their min values are, what their max values are. At initialization, if you set them to 0, you should get number of classes minus 1 versus log c. So you should check that because at initialization, if you're not getting log c, or if the y-axis seems to be off the chart or too close to 0, there's something wrong in your implementation. So it's good to sort of know what your curves are, what space are they supposed to live in when you start implementing these things. And you're going to use this this sanity check for homework 1. I mean, not that you're going to, but it's a good sanity check. So this is loss for one example. Will we sum over n? Yeah, so this is L sub I, the same thing. We're going to sum this over all examples. Okay, one thing I want to note is that we introduced two losses, the multiclass, the softmax or the negative log likelihood loss, and the hinge loss. And this is another way of connecting SVMs and softmax functions. If you see these objects being introduced, basically it's the same model class. They are both linear classifiers. They are both doing matrix multiplication and a bias to give you a score vector. And then what you do with the score differs. In one case, you take max of s sub j minus s sub y plus I plus 1. You're defining a particular hinge loss. In another case, you are exponentiating, normalizing, taking negative log probabilities to compute this loss. This is the model. This is the loss. So both the two are using the same model class. So if you hear arguments that my model is more powerful because I'm using an SVM, or my model is more powerful because I'm using a logistic regression, those are garbage claims. The model class is linear. They're identical. Where they differ in what is the function used to search within that model class. You may end up with two different points in that model class. That's because you're using two different optimization functions, but it is identical model classes. You are linear in your input, and that's the space of things you can represent are identical. You do not have any more representational capacity. Okay, so those are the two things that we mentioned. Here's just a quick recap. You have a data set, you have a scoring function that tells you how well you're doing. We told you what a loss function is. And next time we're going to answer this question, which we have not answered, is, okay, I know how well I'm doing, I know how poorly I'm doing, but how do I search? How do I actually find the optimal W star that minimizes the loss function? And that is exactly what we'll talk about next time. And we'll get into gradient descent and how to compute gradients, which will ultimately take us into backpropagation. Okay, let's stop here.